integral test. I'm going to be honest and say that I only use this as the test of last resort. It annoys me for some reason. I don't know why. I feel like I shouldn't have to go through an integration. It's not like it's hard or anything. It's just, I don't know, it just bugs me. So anyway, if worst comes to worst, then I use it. But if not, I always try to find another test. But it's really not difficult, right? So what the integral test says is if the original series is going to converge if and only if the improper integral converges, right? And remember that the function has to be continuous, positive, and decreasing, and more importantly, you only want to use this test if the function is really easy to integrate, or if you're dealing with LNN type problems. On the test, some of you tried to use the integral test on just something insane, and you were going to use substitution, but your du was not, in other words, you couldn't write a new integral because the derivative had nothing to do with the function that was in the original integrand. So there was a big conflict there. So when that starts happening, that's your red flag. Don't use this test. It's not easy to integrate. So a simple example, n plus 1 over n squared. Alright, so I would rewrite this, and I did, as the integral from 1 to t of n to the minus 2, right, times the quantity n plus 1, and then I distributed it to get this. Alright, and then I cleaned it up a little bit more. I know that n to the minus 1, I'm not going to integrate that and get n to the 0, right? That's bad. This is 1 over n plus n to the minus 2. And so now, integrating this thing, I'm going to have ln n minus 1 over n, so that's the antiderivative of this. And I have to evaluate it from 1 to t. And I went ahead and I plugged my t in here. And don't forget, you also have to plug your 1 in, so it's f of b minus f of a, fundamental theorem of calculus. Now, the natural log of 1 is 0, and the negative of a negative 1 is going to make that a positive 1, but as you're going to see, or as you should already see, that when we plug infinity in here, that's going to blow the whole thing up. So it doesn't matter that we have a plus 1 because we have infinity, right? So when we take the limit of this thing, we end up with infinity, okay? And what that means is that this integral, or the limit of this integral, diverges, and so what we know is that the original series is also going to diverge by the integral test. Here's one with an ln n. Make sure this is in the screen. Okay, so we have ln n over n. Now I see that this is very easy to, and by the way, I'm being very bad here, I should put a dn there. I can see this is very easy to integrate because if this is my u, then du is 1 over n, which is sitting right here. So, you know, you can think of this or break it apart a little bit, not apart, but you know what I mean. Simplify it more to the I as ln n times 1 over n. That way you can see the derivative sitting right there. And so we have to use a little bit of u substitution. So for the greater, right, we need to say u is this, du is that. Everything matches perfect. I went ahead and changed my limits. And now I have to integrate u. So that's just u squared over 2, and if I evaluate it from 0 to ln t, I get ln t squared over 2 minus 0. And again, if I plug infinity in here, I have infinity squared, which is infinity. So we say it diverges by the integral test. That's it.